Okay, here I am again. I'm sorry, this is probably the second day in a row that you've had to suffer my rotten videos. But anyway, I'm still in Brazil, I think. So we're just going to run through one more concept, and this one's a fairly short one. Not too much to add here. And it's got to do with something called the percent theoretical yield. I tell a little story here at the beginning about an accident that happened in Seveso, Italy, where there was an explosion, and up through a stack came a white powder, which nobody thought much about until it was sent off for analysis, and they noticed that people were getting sick and animals were getting sick, and it turned out to be one of the more deadly compounds that are man-made called dioxin. Anyway, what are the chances that a cosmetics company was trying to make dioxin? Well, zero. But obviously something was happening in their reaction. And this happens quite often, where what you think is happening in your beaker is not really happening in your beaker. So we don't often get, or don't always get, exactly what we think, and so it's incumbent on us to know what is our yield, how much of what we think we're getting are we actually getting. We're going to look at this in two ways. Today we're going to look at something called the percent theoretical yield, and later on we're going to look at a more modern concept and something called the atom economy, which is a very simple concept to get across. Anyway, let's take a look at this. I don't want to say too much more about that. There are a couple definitions here. Your theoretical yield, that's what you think you should get, and that's what we've been doing so far with our stoichiometry problems, our limiting reagent problems. That's what you're calculating is the theoretical yield. The experimental yield is what you actually get. So if you're trying to make some kind of a solid material and you scrape the solid out of your beaker, you know how much solid you should get, but you might not necessarily get everything that you expected, okay? Experimental yields are usually smaller than theoretical yields, and I challenge you to come up with 5 or 6 reasons why you think that would be. We'll discuss that next day. Sometimes the experimental yield can be greater than the theoretical. I don't know how that happens. Anyway, you can maybe think of some ideas for that, and some possibilities. The only new thing to add today is this equation that we have at the bottom of page 155. And you'll see, sorry, I'll just organize this. The percent yield is just the relationship between experimental and theoretical. You can see it. You put experimental over theoretical, multiplied by 100. Very simple. Not really much new here today. Note that your yield masses have to be exactly the same. Okay, let's look at a couple examples. Whoops, that's not what we want there. I'm looking for a blank page here with the numbers. And I don't see it. I don't see one. Where is it? Okay, so right here it is. Sorry for my... this is actually the second time I've done this. I noticed the first time I left the focusing on, and it was just too jumpy to see. Okay, so here we go. Here's a problem that I purloined from another textbook. 7 grams of silver nitrate added to a solution containing excess solid KBr. What are the products of the reaction likely to be? Well, as you're probably aware, we're going to need a balanced equation. And so I challenge you to come up with the balanced equation. And so turn off the tape if you want and come up with it. So anyway, we've got silver nitrate, I'm assuming aqueous, plus KBr, that's our other reagent, aqueous, reacts to form. Now, you might look at that and say, well, it could be an addition reaction. It could be, but it's not. It's going to be probably a double displacement reaction where we get silver bromide and we get potassium nitrate. And then you'll notice I haven't put in the states yet. Which one do you think is going to be a different state? And maybe you chose this to be the solid and this to be the aqueous, and you'd be correct because you hopefully recall that all group 1 ions are soluble and all nitrates are soluble. Okay, you check to make sure that it's balanced. I think in this case we are. We're okay. So let's figure out our theoretical yield, part B. We start with 7 grams of silver nitrate. We're going to multiply by 1 mole over its molar mass, which I got to be 172.87. You should check my math because I'm not necessarily on my game today. That's 1 mole of silver bromide. This is our equation factor, and it's got to be there. I know it's 1 over 1, but it's got to be there to show how you've converted to moles of silver bromide. And then we get our mass of silver bromide by multiplying by 187.78 moles of silver bromide over 1 mole of silver bromide. And of course this will all divide out, and when you do the calculation, hopefully in your head, no, I'm just joking, 7.60 grams of silver bromide. So our percent yield, very simply, is going to be what we got, and I gave you that in the question, 7.32. This is very often tacked on the end of a question, either a limiting reagent problem or a stoichiometric question. Anyway, that's what we got. This is what we thought we should get, times 100, and we got 96.3%, which is a pretty high yield, which is good because it contains silver. We don't want it going down the sink or into your pocket. Okay, second example, very quickly, synthesis of sulfuric acid. I'm challenging you to come up with just a review as the formula, H2SO4. Sulfur's conversion of sulfur dioxide to sulfur trioxide, but you knew that. So SO2, gaseous, reacts with oxygen in the air to form SO3. And then you inhale that and you got sulfuric acid in your system. That's not a good thing to do. Don't go around sniffing SO3 or SO2 for that matter. So it says in one run, we took 1.75 kilograms of sulfur dioxide. We got 1.72 kilograms of sulfur trioxide out. What's the percent yield? Okay, so let's go with this. First of all, let's balance this equation. Did you notice it wasn't balanced? Okay, so let's go for this. You can either go through the calculation to show that this is actually 1750 grams of SO2. And in 1 mole of SO2, sulfur is 32, oxygen is 16. So that would be 16, I think it's 64.1 because sulfur is 32.06 grams of SO2. There are 2 moles. Once again, it's a 1-to-1 relationship, SO3 to SO2, but you've got to show it, and I would put in the actual numbers so that people understand where these things are coming from. And then SO3 is going to be 32.06 plus 3 times 16, which is 80.1 grams of SO3 over 1 mole of SO3. And that, my friends, equals 2180 grams, which would be 2.18 kilograms. So my percent yield is 1.75 kilograms over 2.18 kilograms times 100, which is 80.3%. Also fairly high. Okay, there'll be some problems there on the next page, page 157, for you to work on. There's not a whole lot there. There's not really much new to this concept. So there you go. Give those a try. And then if you have more time in class, please work hard on that whole thing. There are a number of review questions in the pages following where you can start preparing for the test that's coming up probably in the next week or so. Okay, thanks a lot and have a great day.